Hello everyone, welcome to Ada. Now we are going to solve this question where you can see we have been asked to calculate the draw the SFD and BMD of the following beam. So let us see how we can do that. We have a 3 UDL between AB, BC and CD. So firstly we'll draw the FBD of the beam and then we'll find the shear forces and bending moments at every point. So following step 1 we will draw the FBD. And for that, we need to convert each of the UDL into a point load. Well, let us say this is A, B, C, D. So the first UDL will be 15 to 200 Newton acting at the midpoint of AB, which will be 1. And the next UDL will also, but the force is acting in the upward direction. So 15 to 2, that also will become 100, but in the upward direction. 1 is the distance because whenever you convert the UDL into a point load, it is just the magnitude of the UDL into the length of the UDL. So 50 into 2 is 100. And it is acting at the center of the UDL, which will be this midpoint of the UDL, which will be, if it is 2 meter, then 1 meter from either side. So the third UDL, which will be the between the C and D, we have 100 Newton, 1 meter from C and 1 meter from T, because the total is 2. So that is how you can draw your FAD. The reaction forces at T is in the upward direction, let us call it FDY. And at A, there are two reaction forces because of the hinge support. So FAX and FAY, let us call them. You can apply the equilibrium condition now, the equilibrium conditions. So equilibrium condition, if you apply, we have three equilibrium conditions. Summation of Fx is 0, which is a summation at horizontal forces. We have summation of vertical forces, which is summation of Fy is 0, and we also have summation at movement at any point is 0. So applying the first condition, you will get that the value of Fx is 0 because there is no another horizontal force. So, and thus applying the second condition, which is the summation of Fy is 0, we have Fay as the vertical force minus 100 plus 100 minus 100 plus Fdy is 0. So it will be Fay plus Fdy is 100. So we have considered the upward forces as positive and downward forces as negative. You can change this, it won't affect your solution. So as you can see, there are, let us call it equation number 1. In the equation number 1, there are two variables, which is Fay and Fdy. And you cannot solve this equation unless you have a second equation, because there are two variables and one equation, you can solve this. So solving it will require another equation, which will come from summation of movement at any point is 0. So let us say we are calculating movement at point A. So we have 100 into 1 as a clockwise movement. So clockwise you will take it as positive and anti-clockwise you will take it as negative. Again you can change this, it won't affect your solution. We have 100 into 1 as a clockwise movement minus 100 into 3 as an anti-clockwise movement because of this B to C UDL force. Also we have an clockwise movement of 100 into, that is total distance because of the CD UDL will become this 100 Newton force is there. So 1 plus 1 plus 1, 3, 4, 5. So it will be 5. And we have the finally the Fdy force, which will act as an anti-clockwise movement, and the total length is 6. So we have this as our equation. We can calculate this. It will be 500 plus 1 600 minus 300 is 300. Divided by 6 is 50. So Fdy will be 50. And you can put this into your first equation. Fay will also come out to be 50. So as you can see, we have found out both the variables, so which is all the reaction forces, that Fdy, Fay and Fax. So Fax comes out to be 0. This comes out to be 50, and Fdy also comes out to be 50. So after calculating the reaction forces, you can now move ahead with your calculation of the shear forces at every point. So shear force at the right of A, so just right of A. So for that, the sign convention you need to understand, and you need to follow the sign convention. You cannot change this according to yourself. So whenever you are considering forces on the left, consider upward forces as positive and downward forces as negative. And whenever you are considering forces on the right, consider upward forces as negative and downward forces as positive. So this is the sign convention for shear force. Shear forces. So what do I mean by that? So let us see shear forces just right of A. So this is just right of A, let us say, this is a cross section. And if you consider force on the left of the it, which is just the reaction at A, which is 50 in the upward direction. So that is why 50 is in the positive, because as you can say, left and upward is positive. In a sign convention, you can say. So this is how you can use your sign convention. So let us see now that you are calculating shear force at V. So what will it become at B is nothing but 50. So this is the this is the cross section B, and consider forces on the left. You have two forces, the force at A and this UDL force between AB. So here 50 minus 100 is minus 50. Shear force at C will become minus 50 plus 100, which is 50, because again consider force on the left, it will be just adding this UDL force of BC, it will give you plus 50. Also we have shear force at D, which will nothing but 50 minus 100 is a minus 50, because if you cross the view somewhere here, so somewhere left of the D, so this is not shear force at D, this is just left of D. So this is just left of D. So this is minus 50, because let us say you across the beam somewhere here. Consider all the forces on the left, it will give you minus 50 as your shear force. Or you can also consider force on the right, which is only one force, which is 50 in the upward direction. So 50 in the upward is negative 50, as you can see in the sign convention, because now we are considered the forces on the right side. So right side upwards is negative. So negative 50 also you can calculate from the right side forces. Either way, you will get minus 50 as your answer at left of the D. And shear force at D will go out to be 0, because there is a reaction at of 50 positive, and minus 50 plus 50 will go out to become 0. So if you draw the shear force diagram according to the values which we have calculated, let us say you are drawing it somewhere. This let us say A, B, C, and D. You have just right of A, it is 50. This is 50. At B it is minus 50, minus 50. At C it is 50 again, and at D it is just left of D it is minus 50, and at D it becomes 0. So it is something like this, because there is a UDL in between, so it will always vary linearly or as an inclined line, not as a constant line, because whenever there is a UDL, shear force will vary as an inclined line. So this is how you can draw your shear force diagram. As you can see, like startingly we have a 50 Newton upward force, and then it will gradually decrease until minus 50 at B. And then because of the UDL again in the upward direction, it will gradually increase up to 50, and it will again gradually decrease up to minus 50 because of the again UDL into downward direction. So that is what your shear force diagram becomes. So a trick is, like, whenever you have some values where the shear force is going to 0, as you can see there are 3 values in our case. So at these values the bending moment will be maximum, because like that is a you can also derive this, that whenever the shear force is 0, the bending moment will be maximum. The the easy way of deriving this is, like, let us just rub this. The easy way of deriving this is nothing but shear force is nothing but dm by dx. So whenever the bending moment will be maximum, or let us say minimum, depends on the sign of the moment, the shear force will be 0, because let us say some function you have f of x and you want it to be maximum or minimum, you just differentiate it and equate it to 0. So that is how you do in calculus. So let us say you want a moment to be maximum or minimum, you will just differentiate it and say that it should be equal to 0. And this dm by dx is nothing but shear force. So shear force should be equal to 0. In order to bending moment to be maximum or minimum at any point, the shear force at that point should be 0. So yeah, let us calculate shear forces at this point also, because we know that at this point the shear force is 0. The shear force is 0 and the bending moment is maximum. We have, if you are considering force on the left, consider clockwise as positive, anti-clockwise as negative, and on the right, the opposite is true. Clockwise is negative, anti-clockwise is positive for the bending moments. Yeah, so we have a bending moment. at A and D is 0 because of the equilibrium condition. You can calculate that also. From the FBD, it will come out to be 0 only because the equilibrium should follow of the beam. And at A and D, it will always give the 0 as the result of the bending moment. And we can calculate that midpoint of AB, which is at this point, because we are saying that at that point, bending moment is going to be maximum from our SFD. So bending moment at, let us say, some point x1, which is we are going to say this is x1, this is x2, this is x3. So at x1, the bending moment will become, let us calculate from the left side only. From the left side, we have a clockwise movement of 50 into 1. So it will be giving you 50 as your value of your bending moment. And it is a clockwise, so it will be positive. So bending moment at B, let us calculate. We have 50 into 2 minus 100 into 1, which will be 0. We have bending moment. Again, we are considered left side forces. So that 100 force was producing an anti-clockwise movement. So that is why we are giving it a negative sign. Let us calculate bending moment at x2 now. We have again forces on the left side, let us consider. So we have 50 into 3 minus 100 into 2. So it will give you again a 50 as the bending moment. So yes, that will be. So bending moment at let us say C, we have bending moment at C. Let us calculate from the forces on the right now. We have 50 into 2 as an anti-clockwise movement, so that is why it should come out to be positive. And 100 into 1 as the clockwise movement, so that is why it is negative, because it is on the right side forces now. So that is why the sign convention will change. So bending moment at x3, considering forces on the right. So anti-clockwise movement of 50, so it is positive 50. So yeah, we have calculated all the bending moments, because bending moment at D will be 0, as we have written at the starting of the calculation only. Let us just verify this x2. So we have this x2, this is our cross section. If you calculate on the right, 50 into 3 minus 100 into 2, again it will become 50. So yeah, we have a 50 at A. At A we have 0. At this point, this midpoint, we have a 50. Again we have 0. Again we have 50. Again we have 0 at C. So this is C, this is B, this is A, this is D. Midpoint we have 50. Midpoint again we have 50. So somehow this will be viewer. Okay, this is should be 182. At x2, 102 is 253, 150, so it should be minus 50 area. Minus 50 at x2, that is what we calculated wrongly. So it should somehow go like this. Yeah. And it is a parabola because the shear force is varying linearly. So this is an inclined line. So that is why it is an parabola. So whenever there is a UDL, the shear force will vary as an inclined line, and the UDL will vary as the bending moment will vary as a parabola. Because of this condition also, that shear force is nothing but dm by dx. So you can just put shear force as some constant, then you will get the variation of bending moment as an inclined line or a line. And you can put this variation as a cx plus d, which is line, and you will get the moment variation as a parabola. So you can remember this also, or you can derive this also. This is how we can solve this question. Thank you.